Yeah, thank you. To be still present, I'm the last one for today. I talk about more practical investigation about um, uh, optimizing the hydrogen resistivity of ultra-high strength screws. Was more the thesis of Mr. Elsayed, his PhD thesis. I'm going to present also Milos Dukic reviewed this work. What are ultra high strength steels, rod steels for fasteners? Is my introduction. We selected two types of steels for producing ultra high strength screws. It was 20 manganese silicon, quenched and tempered, as well as chrome molybdenum vanadium, quenched and tempered and or tempered. The methodology I will explain you then later on. The results and our further research on our developed method. Well, ultra high strength steel screws is a part of the of a lightweight construction, where often is the problem that the restriction of the strength of the screws is the hydrogen embrittlement problem, which is limited to 12.9 normally, or for binetic microstructure going up to 16.8. Our goals were to establish a reliable test method to evaluate the hydrogen susceptibility of different ultra high strength screw steels and to optimize the microstructure via different heat treatments to get the high hydrogen embrittlement resistivity. Yeah, here again our two steels. 20 manganese silicon is quite nice. It's a quite cheap alloy and can be used for a so-called quench and partition heat treatment. And the second one is quite a common one, chromium, molybdenum, vanadium. The goal here was to reach the strength class of 16.8 via these two different heat treatments. Yeah, we choose the ASTM incremental step load test to develop or to reach our goals. Probably you know it. It works via the so-called threshold. You make a stepwise loading, and as soon as you get invariant to the loading rate, you get the threshold value which you can use for design or for to optimize your heat treatment. And this a protocol according to ASTM is depending just on the hardness of the steel. Yeah, this is our development. It's maybe not really new. It is a electrochemical cell which is implemented in a tensile test machine. And yeah, you see here just a tensile sample of the rod steel, the counter electrode, the reference electrode to get stable loading current or a constant potential for the hydrogen in situ loading. Here are some of the advantages we evaluated. Well, of high importance is that there's very good insulation of the tensile specimen in the cell, and the core elements are here for sure. The adapters, which must have quite a stable coating, which is resistant to the electrolyte, to acidic or basic substances. And here we proved that, okay, we get quite a stable signal. We choose minus 1.1 volts against the silver chloride reference electrode. And yeah, as I told, we used 30 and 60 hours testing protocol. Yeah, the first steel, 20 manganese silicon, quenched and partitioned. Probably you have heard about partitioning, meaning that you cool, you quench down between martensitic start and finish, and you do an additional partitioning step to stabilize the retained austenite and to gain some ferritic bainite. Here we did a physical simulation of this heat treatment in the dilatometer. Yeah, what was the outcome of different quenching and partitioning parameters? It's not too much influence on the mechanical. Yeah, sorry, the pointer doesn't work. On the mechanical parameters, not too much on the hardness. Also, the hydrogen content with TDS showing just comparable shallow and deep traps. Yes, the result of our optimization is bottom left. Bottom left, it turned out that a long partitioning time here, QP2, showing the lowest hydrogen index. Yeah, this was our practical outcome to optimize this steel against the hydrogen embrittlement. Microstructure is quite complex. It is martensitic matrix. We have retained austenite in blocks. Excuse me that I cannot show it. A block here, retained austenite, and film retained austenite evaluated with XRD. Yeah, also we were surprised that the retained austenite is 10% or more, was due to the very thin filmy retained austenite films. Yeah, the fracture is starting intergranular and turns on to quasi-cleavage plus microvoid coalescence and ending with microvoid coalescence. There is no correlation visible here to the retained austenite distribution. Yeah, this is the nice outcome that we have a quite low hydrogen embrittlement index with this long partitioning time. As you see here, the threshold in the incremental step load test is quite high. So this has a nice potential for these screws. Yeah, this is already published by Elsayed. If you are interested further in this optimization of quenching and partitioning screw steels. The second alloy is quite a common one, chromium, molybdenum, vanadium. Here exist two common types of heat treatment. It is the quenching and tempering, here shown below right, and the austempering, where you quench in the area or below the metastatic start temperature and keep it. Yeah, it's visible that the austempering is quite nice. And this IP4, IP5, 50 degrees below the metastatic start, increasing the tensile strength as well as the ductility. Well, for the austempered, the hydrogen permeation is higher, as well as the diffusion coefficient in comparison to quenched and tempered. The hydrogen content is again quite similar. Yeah, what was a special effect we found that with a longer protocol, where you choose the nice behavior of this austempered microstructure, loose in the threshold stress. This was not very nice, but probably is going to filling up the weak traps, as was already mentioned from Professor Debova on Monday. Yeah, microstructure, quenched and tempered is a tempered martensite, and austempering is tempered martensite, upper bainite, and the most wishful for hydrogen is the lower bainite microstructure of these alloy. Also, we made a TEM analysis. We found that we have different precipitations, especially with the austempered. We have a quasi globular MC and M3C with low diameter and high density in comparison to the other heat treatments. And the fracture is intergranular micro void coalescence for the quenched and tempered, as well as intergranular and quasi cleavage for the austempered microstructures. Yeah, this is the result. Here again, if we make loading for a longer protocol for 60 hours, the hydrogen index is increasing. Well, the summary: hydrogen resistant microstructure for quenched and tempered steel is a stable retained austenite with a ferritic bainite, or suggestible as a long partitioning time. The strength class 12.9 could be reached with a hydrogen embrittlement index of 30%. For chromium, molybdenum, vanadium, the hydrogen resistant microstructure is austempered lower bainite fine globular precipitates. This is wishful to reach the 16.9 strength class with a low hydrogen index. And well, here below you see that we would like to develop further this method, this simple method for to optimize screws or also other sheets against hydrogen embrittlement. Thank you.